Okay, so this was all we did last time. Now we will move on to the case when we have a forcing term. So here we are. Forced vibration. Application of external force to a freely vibrating system modifies the vibration and produces what is called as forced vibration. So the model, background model, just to remind those who were not there in the class yesterday, that there is a spring and a mass is attached at the bottom of a spring. So just a quick idea. So here is a mass, and then because spring, there is a restoring force of minus KL, the natural length of a spring, and an mg acting downwards. These two forces will balance each other. Then further, if I apply external force and pull this mass downwards with a displacement y, then we will have vibration in this spring, and this mass will be moving up and down, up and down. Now we have seen last time that it ends up in this differential equation with a y prime term also, which is coming due to air resistance, resistive forces in the nature. So we had a model, yesterday we had a model y double prime plus c over my prime. Was it plus or minus? And then you had k over m y equals to ft, external force. This was the entire model. Is there a minus sign or plus sign here? Minus? Minus because of damping. Okay. So this one should be minus. So this was the differential equation. Now we are ignoring the resistive forces and we try to see what happens if the external force is periodic. So whenever you see a y prime term in a differential equation, that will cause damping. Damping means eventually these oscillation will die out, because there is some force external which is interfering in the oscillation or stopping the spring in some sense. So now this is the model we have. External force, we call it periodic because it involves cosine. So this, if this constant remains same, f naught over m, then it will be acting periodically. It will be sometimes zero, sometimes non-zero, and it's a periodic force acting on the mass. Okay, so now we want to see what will be the behavior of a solution. Well, if there is no term like this, it is basically a simple harmonic motion, right? If this term is not there, it is SHM. So lambda square plus omega square is 0. So that we are trying to solve associated homogeneous problem. Then lambda will turn out to be plus minus omega I. So you will have your associated homogeneous solution, and it depends on time. So let's take here t is equals to c1 cosine omega t plus c2 sine omega t. So that's a solution for homogeneous problem. For a particular solution, I have to either I can use variation of parameter, or I can use method of undetermined coefficient, because it's a non-homogeneous second order differential equation. Now since the right hand side is a nice function of cosine, we can use method of undetermined coefficient here. So what do you think will be the guess of particular solution? So what should be the guess? X is not at all independent. So let me write it down. So you are saying ZT, I should take a guess as there is no exponential here.
Yeah, so it's just
A, then tell me what will be the guess of particular solution. A cosine will have this angle, right, which is there on the right hand side. A cosine gamma t plus B sine gamma t, provided what? You have to check something, like something is not a root or something like that. So you will check which one is not a root of this. Gamma is gamma plus minus gamma I, whether that is a root of this characteristic polynomial or not, right? If it is a root, then you multiply by t. If it is not a root, you won't. So we are assuming gamma is not equals to omega. Because if gamma is equals to omega, then this is a root of characteristic polynomial and I have to multiply the entire expression by t. Okay, so we are assuming this. Now let's plug this back in the differential equation. Z double prime t plus omega square zt should satisfy, z should satisfy this differential equation, because zt is a particular solution. So zt will satisfy this. Now what is z double prime? Okay, let's do z prime. Negative a gamma cosine gamma t plus b gamma or sine gamma t, sorry, and then the next term will be cosine gamma t. So that's a one derivative here, plus omega square. There is no derivative here, so we will just place the function a cosine gamma t plus b sine gamma t is equals to f naught over m cosine gamma t. We still have to differentiate this once. Minus a gamma square cosine gamma t. From here we get negative b gamma square sine gamma t plus omega square a cosine gamma t plus b omega square sine gamma t is equals to f naught over m cosine gamma t. Okay, now let's collect all sine and cosine term. So cosine term, this is a cosine term here, this one is a cosine term. So we have minus a gamma square plus omega square a to be equals to f naught over m. And the next one will be 0. Now if this is 0, that will imply, this equation will imply what? B times omega square minus gamma square is 0. right? Now since omega is not equals to gamma, this is not 0, so B has to be 0. Now what about this one? This one gives us A. The first equation will imply A times omega square minus gamma square is F0 over M, and that will imply A is nothing but, since this is non-zero, I can divide by this. Omega square minus gamma square, and this whole stuff is in the denominator. F0 divide by this. Okay, let me write it more clearly. F0 divided by this. So this is A. This is A. B is 0. Now what is a particular solution? A cosine gamma t plus B sine gamma t. So ZT here will be A surviving, right? So we only left with here F0 over M omega square minus gamma square times this. Okay, so let me put that page together here so that those who are copying. So ZT is A is F0 over M omega square minus gamma square cosine gamma t. So that's a particular solution. So the total solution of this differential equation, forced periodic external force, is we start with C1 cosine omega t plus C2 sine omega t plus this term here, F0 over M omega square minus gamma square cosine gamma t. Now in your textbook, if you read these sections, there are a couple of terminologies called resonance and transient state, steady state of a solution. What they are basically in that they are saying is transient. Transient means what? When this, what happens when time it's die out, right? What happens when when time becomes larger and larger, what would be happening to the solution? What eventually the solution will be looking like? That's a transient state. Steady state is when you have so the thing is, when you just consider the homogeneous part of a solution, then you are looking at a steady state. When you add the particular solution, you're looking at a transient state of a solution. So there are web work assignments here. So if we, now by the way, I am planning to change the due date of these 26 to 24 because these will be coming in your exam. Okay, and others are till 23, these are straightforward. You just have to use the formula, but these one will be due before exam. We will have up till here on Friday solution of IV, not solution of IV, 6.1 till here. So, but they all are open. So let me go to the free, not free we have done yesterday, forced. Let me pick any problem of this. So this is an example of an undamped forced oscillation, undamped because no y prime term here, right? Where the phenomena of pure resonance occur. So if you try to solve this differential equation, what are the roots of characteristic polynomial here? Plus or minus 2i. So that means here you have a 2 here sitting, right, in sine. So you have to multiply it by time to find the particular solution of this. And z will involve a time thing in that. So you can see with initial condition being 0 here. Okay, let's do it. Why not? Why to just write it down, so it would be much easier to then. So this is the solution of the above problem. Okay, so now coming to this example. As you said just now, lambda square plus 2 is 0 will imply, well, actually not 2 here, it should be 4. So I should have lambda square minus 4, that will imply lambda is plus minus 2i. So that tells us the homogeneous part will be a cosine 2t plus, or if you don't want to confuse it, let's try C1, C2 only for homogeneous solution. C1 cosine 2t, C2 sine 2t. And then the guess for a particular solution will be t you will multiply in cosine 2t plus b sine 2t. So this time, since because your 2 plus minus 2i is a root of Cp and 2 is appearing right here. So that's the reason you will multiply by t, so that you get values of a and b. Okay, now plug this back in differential equation. Z double prime t plus 4zt should be equals to 16 sine 2t. Let's see what will happen to the solution. I will not apply these initial conditions here. I will apply these conditions when I'll add my particular solution in my homogeneous solution. Okay, so don't just plug it here and say, oh, my C1, C2 is gone. C1, C2 will be gone if you just apply it here. Okay, so let's do this. So we have t 2 times negative a sine 2t plus a cosine 2t product rule plus 2tb cosine 2t and plus b sine 2t. This is just once I have done the derivative of z. Again I have to do 4 times ta cosine 2t plus bt sine 2t. So I am multiplying t in both the terms and then I have multiplied by 4, and this whole thing should be equals to 16 sine 2t. Okay, we have to still do one more differentiation here. So this will be minus 4t a cosine 2t minus 2a cosine 2t minus 2a sine 2t, and this one is plus 2b cosine 2t minus 4tb sine 2t. And differentiation of this I think I took into account. Right. So this gave me 2 terms, this gave me 1 term, this gave me this term and this term, this further will give me 1 more term, plus 2b cosine 2t plus 4ta cosine 2t plus 4bt sine 2t is equals to 16 sine 2t. Okay, now let's see what is cancelling. 4ta A cosine 2t. For t b sine 2t. T terms are going, because this was the whole purpose of incorporating t. So this is gone, this is gone. Cosine terms I will be marking in blue. So this is cosine term. Oh, they are also going. And one more is there. This. Okay. No, this has A, this has B, so they are not going. Okay, these are 3. And sine term will be, let's mark it with another color. Say this one. Sine will be having, we are just having one term for sine.
Should your second cosine up there be a sine from the first term when you do your... So
I multiplied 4 here, 4 here.
Right, but...
this one?
No, the one above it.
This one?
Yeah.
This is just, I have done a differentiation here. T differentiation. Oh, that's right.
You have your cosine and
Sine, right.
That should be sine, right?
That should be sine. Okay, so that means this term is together and this term is together with the sine term. Okay. Right. I mean, we will check this answer by putting in a web work. So let's move on. So A will be here, minus 4A is 16, so that will imply A has to be negative 4. And 4B is 0, imply B is 0. Okay, so A is negative 4 and A is again coming with the cosine. So as you can see now, even though the external force was periodic with sine, your particular solution does not involve sine. So Zt turns out to be, in this situation, minus 4t cosine 2t. Okay, so the total solution is, a general solution I should say, is C1 cosine 2t plus C2 sine 2t minus 4t cosine 2t. Now let's plug the initial condition. Y at 0, well, they had terminology x, but it's one and the same thing. Is 0, so that means if I plug 0 here, this term is gone, this will survive. So C1 has to be 0. Okay, let's do y prime here. Y prime t is negative 2 C1 cosine 2t, sine 2t. I don't know why I keep taking this cosine terms like that. Okay, and then this one has 2c2 cosine 2t, and this one again product rule, minus 4 cosine 2t, and the term which will involve minus become plus sine 2t. So at 0, this is gone, this is gone, this will survive, right? So y prime at 0 is 0 will imply 2c2 is 4, right? So this will imply c2 is 2. Okay, so if C2 is 2, then your solution eventually turns out to be sine 2t minus 4t cosine 2t. right? So let's see whether the solution is satisfying. What was the 2 sine 2t minus 4t cosine 2t? Okay. Cosine 2t, right?
Yeah.
Cosine 2t. And we have to be careful that if the independent is t variable, we will keep t, and otherwise, right. So this is the solution of undamped forced oscillation. Now, why are they saying here pure resonance will occur? One way of checking this idea of resonance is, you have seen here in this example, your frequency of external force, which was here 2, is same as the polynomial roots which you get here. They matches up. And because of that, you had to incorporate a t in this, in the particular solution. So when omega is equals to gamma in the previous situation, which we are doing here. So if omega is, this is a case when we did omega is not equals to gamma. If omega is equals to gamma, it's a pure resonance case. If omega is not equals to gamma, it's not. Okay, so there is I always, like every semester I comment this thing, that there is a YouTube video on Tacoma Bridge, and that was the one, the construction of that bridge basically failed. Engineers were constructing and it was failed, and I think maybe the day of launch only they figured it out. It was resonance, and the frequency by which people were moving matches up with the frequency of the bridge, the way, and bridge started moving. So I mean, it was mainly they had to basically close this bridge eventually, but what was happening was this resonance.
It was the wind, right?
It was a wind, but they didn't take account of all the forces, the way they were constructing it.
As you can see,
So
this bridge was
length,
exceptionally
width,
long and
center,
narrow,
start
over half a
of the
mile long,
construction,
only during the entire useful life of the
I would not, so see,
2 miles per
here
hour.
they have mentioned this, but this was exactly happening.
The roadway.
To now, in this one,
It's
people are not
remarkable,
there, but
this.
it was shown when people were there how they have to move backward, some have to move forward to stabilize themselves on the bridge. But this has to eventually stop.
was
But
frightened.
it's good to see how much it can. It's important to be very careful about this feature of resonance. Okay, so
The
it's
bridge was
very
rebuilt
practical
using a stiffening truss
concept.
instead of girders. The new bridge is completely stable.
Watch this and see what's going on. It's